This sample problem deals with rotational dynamics. We have a merry-go-round, which we'll assume is a uniform disk. Ignore any handles on a real merry-go-round. This is a physics problem, just a flat disk, diameter 5 meters, mass of 120 kilograms. There's some force that we don't know, but it's acting tangentially on the disk, and it's going to make the merry-go-round spin faster. It starts at rest, so 0 revolutions per minute, and we end up at 12 revolutions per minute in a time span of 15 seconds. So our calculations will be to calculate the angular acceleration in units of radians per second, calculate the magnitude of the force that's creating this acceleration, and calculate the linear distance in meters for some little speck of dust that sits out on the rim of the merry-go-round and during this 15-second time interval. So let's take these one at a time. First, the angular acceleration. We make a sketch of the problem, and perhaps we read the problem twice. So 5 meters for the diameter, mass of 120 kilograms. Here's our force that's tangential to the disk. And we can go on now to the calculations. For the angular acceleration, we need to know how much has the angular velocity changed and what was the time period where that change occurred. We're going to assume the force is constant. We have an average angular acceleration that'll be a constant angular acceleration in this case, but constant angular acceleration. So angular velocity, omega, the final minus the initial, divided by the time interval is what we're looking for. Let's calculate the final angular velocity, omega. So 12 revolutions per minute is where we ended up. We need to get to radians per second. So I'm going to convert a revolution into 2 pi radians, and I'm going to convert 1 minute into 60 seconds. Notice the units cancel here, the minutes cancel, the revolutions cancel. And check this on your calculator. I came up with 1.2566 radians per second. So our alpha, our angular acceleration, is the change in omega divided by the 15 seconds. I keep 4 digits on intermediate results I might use later in a calculation and round to 3 digits for an answer to the question of what I'm supposed to calculate. So 8.38 times 10 to the minus 2 radians per second squared. On to this next part that involves dynamics, dealing with the force that acts on the disk, and especially we need to formulate this as torque since we're doing a rotational problem. So you're familiar with the linear kinematic equations where the acceleration is constant. This is for a straight line. When we're dealing with rotational motion, we need to switch the variables. Omega takes the place of velocity, theta takes the place of our position, and alpha takes the place of acceleration. T stays the same symbol. So in F equals ma, when we're moving in a straight line, when we're moving in rotation, torque equals rotational inertia multiplied by the angular acceleration. Torque is equivalent to force in the rotation system. Rotational inertia is equivalent to mass, and angular acceleration takes the place of linear acceleration. For all of these, there's a radius involved in changing force to torque, mass into rotational inertia, and it's more complicated than just multiplying by r. You have to worry on how the mass is distributed, and we'll go on. But torque is tau in the symbol system I used. I represents rotational inertia, and then alpha for the angular acceleration. Torque is the force that's perpendicular multiplied by the lever arm. Perpendicular what? Perpendicular to the lever arm. The lever arm extends from the axis of rotation out to where the force is applied. So torque equals this perpendicular force multiplied by a radius. And the rotational inertia for a uniform disk, we can calculate this I, 0.5 times the mass of the disk times the radius of the disk squared. this formula for I will be different for different shapes. Your physics textbook should have a table in it that has the shape pictured and then the formula for the rotational inertia. Our linear velocity is calculated by taking the radius out to the point of interest where we want to know the linear velocity, multiplied by the angular velocity. And for the arc length, the path covered by an object at some distance r from the axis, we take the radius times the central angle theta. How far has the object turned? So that's what we're going to be working with. Well, for the angular acceleration, again, we have this calculation. We've come up with that value so we can go further. And we want to calculate the magnitude of the force. Well, to calculate the force, there's a few steps. We've already done the angular acceleration. Then we're going to calculate a value for this shape, for the disk. We're given its mass and diameter. We can get radius from that. We're going to calculate the torque, and that will let us calculate the force. So we're kind of working backwards here. The acceleration is caused by torque. Torque is caused by a force acting at a certain radius. So here we go. The uniform disk, 5 meters, mass of 120 kilograms. We calculated changed the units from what we were given to the omega being in radians per second here. Previous slide, we calculated the angular acceleration. And now we want to do this calculation for I, 0.5 mr squared, 0.5, 120 kilograms for the mass of the disk, 5 meters for the diameter, 2.5 meters for the radius, so 375 kilograms meters squared. That's the units for rotational inertia. And then we have torque equals I times alpha. We find the I, we found the alpha earlier. So multiplying those together, our torque is 31.41 newtons times meters. And again, I'm keeping 4 digits here for an intermediate result. So torque is this perpendicular force times the lever arm. 31.41 newton meters for the torque, our force that's unknown, and 2.5 meters for the radius. I have a question for you. As we started this problem, we said that there was a force tangential to the disk acting on the system. I'll go back up to this slide where the picture is. The force is tangential to the disk. Is this force perpendicular to the lever arm? Yes, you can imagine a lever arm here that extends from where this force is applied back to the center of the circle. A vector, a line that's tangent to the circle, is perpendicular to the radius line. So we've met the qualifications for having this perpendicular force. So I'm back here. So perpendicular force times 2.5 meters is correct. It's proper. Doing that division, I get 12.56 newtons for the force, intermediate result, and then round it to 12.6 newtons. Okay, what's the distance that a bit of dust has traveled on the rim? Well, we can get to the kinematic equations for rotation. The theta is our position, and we get 15 seconds of motion is what we were specified. We calculated the angular acceleration earlier. 15 seconds, don't forget the square in this kinematic equation. I came up with 9.424 radians for the final theta. We've progressed, we've turned 9.424 radians. What we're asked for is the linear distance, not the radians, but in meters. S equals r theta. S is the arc length around the circumference of our circle. R is our radius, theta is the angle that we've turned, and this works even though theta is more than 2 pi. We've gone more than 1 revolution. That's fine. It's r times theta, and we get 23.6 meters. That's what we're asked for the question, the linear distance traveled. So there you have a summary of how to do some simple calculations with rotational dynamics, kinematics. I have many more videos in physics and astronomy. They're listed on my simple website, gpclements.com. And the videos are grouped by topic, and it's an annotated list that has a title, and that title is a link directly to YouTube. You don't have to search on YouTube for my videos. You can go to my website and directly get to YouTube by clicking on the links that I've put in there. The annotation also includes the number of minutes for the video and a description of the video, the content. All this content's free. You can't resell it to somebody else, but it's free. And you do not give me your name or your email address, anything. And my website does not put cookies on your computer. Ask your instructor if you have questions.